Hello, friends. Welcome back. Or if this is the first time you found your way here, welcome. I'm so glad you're here tonight. Look up on any clear evening, and you'll find it the brightest point of light in the sky, not a star, but a planet, close enough to feel familiar, beautiful enough to make you pause. And yet, every rocket we've ever seriously planned to send humans to has pointed the other way. Why would we sail past the nearest harbor into deeper, darker water? Before we drift into that question together, if these quiet journeys through science bring you some comfort, some wonder, or just a soft place to rest your mind, at the end of the day, you might like to stay a while. A gentle tap on the like button means the world truly. And if you'd like more nights like this, subscribe and ring the little bell not for noise, but so the next quiet story can find you again, right when you need it. Now, let's drift. There is something quietly beautiful about the evening star. For thousands of years, humans watched it rise before sunset and linger after dawn, and they gave it many names. The Babylonians called it Ishtar, goddess of love and war, appearing twice, once at dusk, once at dawn, as if the sky itself couldn't decide where she belonged. The ancient Greeks thought it was two separate stars, Phosphorus, the light bringer of morning, Hesperus, the soft lamp of evening. It took centuries to understand they were the same object, the same world circling the sun, just inside our own orbit, catching light, at angles we couldn't quite predict. That world is Venus. And for most of human history, Venus was the great mystery of the inner solar system. It hung so close, closer than Mars, closer than Jupiter, closer than anything except the moon and the sun itself. And yet it revealed almost nothing. No surface markings, no moons. Just a featureless white disk wrapped in cloud, as if the planet had drawn a curtain around itself and refused to be seen. Scientists of the 18th and 19th centuries filled that silence with imagination. In 1918, the Swedish chemist Svante Arrhenius, the same man who first calculated the greenhouse effect of CO2, a genuinely brilliant mind, published his theory of Venus. He believed the thick clouds meant moisture, moisture meant water, water meant life. He wrote quite confidently that Venus was probably covered in swamps and tropical vegetation, something like Earth during the Carboniferous period 300 million years ago. Warm, wet, lush, teeming with primitive creatures. He imagined fern forests stretching across a planet perpetually shrouded in warm rain. He was not alone. Respected astronomers agreed. Popular science magazines of the early 20th century describe Venus as a kind of second Earth, younger, wilder, perhaps even more alive. And here is where the story becomes quietly heartbreaking. Because every single one of those beautiful imaginings was wrong. Not slightly wrong, not directionally wrong, catastrophically, completely, irreversibly wrong. In 1962, NASA's Mariner 2 spacecraft became the first probe to successfully fly past another planet. Its target, Venus. And what it measured as it swept within 35,000 kilometers of that cloud-wrapped world, those numbers landed on scientists like cold water. The surface temperature of Venus was not warm and tropical. It was 465 degrees Celsius. That is hotter than the surface of Mercury, the planet closest to the sun. It is hot enough to melt lead, hot enough to incinerate paper in seconds, hot enough that any water, any ocean, any cloud of rain would have boiled away billions of years ago, leaving nothing but a scorched, airless desert, wrapped in a sky of carbon dioxide so thick it crushes everything beneath it. The atmospheric pressure at the surface of Venus is 92 times greater than Earth's. If you were somehow transported to the Venusian surface, which, to be clear, no human technology today could sustain, for more than minutes, the air itself would press in on you, like the deep ocean floor 900 meters below the surface of the sea. The Soviets learned this the hard way. Between 1970 and 1982, the Soviet space program launched a series of spacecraft called Venera Russian for Venus. Each one was engineered to survive the descent through that crushing, scorching atmosphere. The scientists knew it would be brutal. They built their landers like small submarines, thick metal shells, pressure vessels insulated against heat. They were proud of their engineering, and on some level, they should have been. Venera 7 in 1970 was the first spacecraft in history to successfully land on another planet and transmit data back to Earth. It survived for 23 minutes. Venera 9 in 1975 sent back the first photographs from the surface of another world, grainy, haunting images of a rocky plain strewn with sharp, angular slabs, like a landscape that had never known, weather never known, wind soft enough to round an edge. It survived for 53 minutes before the heat and pressure ended the transmission. The most successful Venera landers lasted just over 2 hours. 2 hours. On a planet just 38 million kilometers away at its closest approach. Think about what that means. We have rovers on Mars that have been operating for years. Opportunity lasted nearly 15 years. Curiosity is still driving, still drilling, still sending postcards home. The Mars rovers became almost like companions, things we named, things we grieved when they went quiet. But Venus eats spacecraft, like the ocean eats paper. And so, somewhere in the long arc of space exploration, a quiet decision was made. Not a single dramatic meeting, not one bold declaration, but a gradual collective turning away from the bright planet, the close planet, the planet that had once seemed so full of promise, and toward the rust-colored world further out. Mars. Always a little dimmer, always a little further, always asking more of us in time and distance and fuel. But Mars whispered something Venus never could. Mars whispered, "Come closer. I have things to show you." And here is the strange, beautiful irony at the heart of everything we'll explore tonight. Venus is closer to Earth than Mars, in simple distance by raw numbers on a chart. At its closest, Venus comes within about 38 million kilometers of us. Mars, at its closest approach, is still 54 to 55 million kilometers away. By the logic of a roadmap, Venus should be the obvious first stop. But space is not a roadmap. Space is a dance planets moving in their orbits at different speeds, at different angles, around a star that pulls everything into curves. And in that dance, distance on a chart means almost nothing compared to the energy required to reach a destination, the window of time available to launch the conditions waiting on the other side of the journey. Have you ever looked up at Venus on a clear night and really wondered what it might have been like if things had gone differently? If Venus had kept its oceans, if the greenhouse effect had never spiraled out of control? Scientists believe Venus and Earth were once remarkably similar. Same size, nearly. Venus is about 95% the diameter of Earth. Same mass within a few percent. Same rocky composition. Same distance from the stellar neighborhood where liquid water can exist. They formed from the same cloud of gas and dust, roughly 4.5 billion years ago, in the same neighborhood of the early solar system. For perhaps the first billion years of their existence, they may have been almost twins, both warm, both possibly wet, both candidates for what we now call habitability. And then something went wrong on Venus. The leading theory, still debated, still refined, is that Venus receives slightly more solar energy than Earth, enough to begin evaporating any oceans it may have had. Water vapor is itself a greenhouse gas. More water vapor meant more warming. More warming meant more evaporation. A feedback loop with no off switch. The oceans boiled away. The hydrogen escaped into space. The carbon dioxide, which on Earth is largely locked into rocks and oceans and living things, had nowhere to go. So it built up in the atmosphere layer by layer over millions of years until it created the crushing, roasting hell we see today. Scientists call this a runaway greenhouse effect. And here is a thought that is worth sitting with quietly for a moment. The same process running in a milder form is what climate scientists warn about when they discuss Earth's future under unchecked carbon emissions. Venus is not just a planet. Venus is a warning written in 4 billion years of atmospheric history, a message from our sister world pressed into the geological record like a letter we're only now learning to read. That's part of what makes Venus scientifically valuable even now, even without human missions. The European Space Agency's Venus Express orbited Venus from 2006 to 2014, studying its atmosphere in extraordinary detail. Japan's Akatsuki orbiter has been circling Venus since 2015, watching the superrotation of its atmosphere, winds that circle the entire planet in just 4 Earth days. Even though the planet itself rotates so slowly that a Venusian day is longer than a Venusian year. Let that settle for a moment. On Venus, you can watch the sun rise, and before the sun sets, the year is already over. It rotates backward compared to most planets in our solar system so slowly that astronomers still debate whether its rotation was reversed by a massive ancient collision or gradually twisted by the gravitational push and pull of the sun and its own thick atmosphere. Venus keeps its secrets not by hiding them, but by making them almost impossible to reach. And so we turn slowly like the planets themselves, away from the familiar brightness of the evening star, away from the closest harbor in the solar system, and towards something harder, further colder, something that has left its doors open, something that has let us read its story, layer by layer, crater by crater, dried riverbed by dried riverbed, across hundreds of millions of years of silence. The next question isn't just about distance or temperature or atmospheric pressure. It goes deeper than that. It goes into the mathematics of space travel itself, the hidden geometry that governs every rocket ever launched, every mission ever planned, every dream of another world ever put to paper. Because it turns out that closer is one of the most misleading words in the entire vocabulary of space exploration. And understanding why, really understanding the elegant counterintuitive physics behind it, changes everything about how you see the solar system and why we go where we go. Imagine you're standing at the edge of a river. On the other side, maybe 30 meters away, there's a path you want to reach. Simple enough 30 meters, you can almost shout across it. But the river is running fast at an angle pulling everything downstream. If you jump straight across, the current carries you sideways, and you land somewhere entirely different from where you aimed. To reach exactly where you want to go, you have to aim upstream. You have to account for the current. You have to think not about where things are, but about where things will be by the time you arrive. This is the quiet secret at the heart of every space mission ever flown. And it is the reason that closer, that simple reassuring word, means almost nothing in the vocabulary of orbital mechanics. Now, before we go deeper, if these slow journeys through science and space are something you find yourself returning to something that helps the night feel a little softer, a little wider, I'd love for you to stay. A gentle like on this video tells me these stories are reaching you. And subscribing means the next one will find you without you having to go looking. It's a small thing, but it genuinely means everything. Now back to the river and the mathematics that govern every dream of leaving Earth. In 1925, a German engineer named Walter Hohmann published a paper that almost no one read at the time. It was called Die Erreichbarkeit der Himmelskörper, the attainability of celestial bodies. He was working in an era before digital computers, before space programs existed in any meaningful sense, before rockets had even demonstrated they could reliably leave the ground. And yet, sitting at a desk in Weimar-era Germany, Walter Hohmann worked out the most fuel-efficient path between any two orbiting bodies in the solar system. The answer, he found, was elegant counterintuitive and has governed every planetary mission ever launched since. He called it an elliptical transfer orbit. We call it in his honor the Hohmann transfer. Here is how it works, and I want you to hold this idea gently, because it is one of those ideas that once understood changes how you see the entire solar system. Every planet orbits the sun in an ellipse, a stretched circle. Earth moves along its ellipse at roughly 29.8 kilometers per second. Mars moves along its wider, slower ellipse at about 24.1 kilometers per second. Venus, closer to the sun, moves faster, about 35 kilometers per second. To travel from Earth to another planet, a spacecraft doesn't simply point itself at the target and fire its engines until it arrives. That would require an almost impossible amount of fuel. Instead, the spacecraft uses the sun's gravity as a kind of infrastructure. It fires its engines once to leave Earth's orbit, enters a long, curving arc that intersects with the target planet's orbit, and coasts mostly unpowered through the rest of the journey. The shape of that arc, that coasting ellipse, is everything. To reach Mars, a spacecraft fires its engines to speed up, pushing into a larger orbit that swings outward toward Mars. The whole journey takes roughly 6 to 9 months, depending on the specific geometry of the launch window. The spacecraft and Mars arrive at the same point in space at the same time, like two trains converging on a single station from different directions, timed to meet within a margin of seconds after traveling hundreds of millions of kilometers. Now, here is where Venus becomes complicated in a way that surprises almost everyone when they first encounter it. To reach Venus, a spacecraft must actually slow down, not speed up. Slow down. Because Venus is closer to the Sun, its orbit is smaller and faster than Earth's. To fall inward toward Venus, a spacecraft has to reduce its velocity relative to Earth's orbital motion. It has to push against its own forward momentum, bleeding off speed deliberately, so that it falls into a smaller ellipse that intersects Venus's path. This seems simple enough, but the energy required to slow down in space is just as significant as the energy required to speed up. Rockets don't have brakes. They have engines, and every burn of an engine costs fuel, and fuel has mass, and mass makes everything harder and more expensive. The total energy budget for a Mars mission and a Venus mission, when properly calculated, is surprisingly similar. And in some trajectory configurations, Venus actually costs more, not less. Let that settle for a moment. The closer planet can cost more to reach. This is the kind of fact that makes people stop and reconsider their intuitions about space. It is the place where common sense and orbital mechanics part ways quietly without drama, like two rivers diverging in a flat landscape. But the fuel equation is only part of the story. There is another variable that shapes mission planning even more fundamentally than the energy required to travel, and that is the launch window. A launch window is the period of time during which a spacecraft can be launched and still arrive at its destination on the desired trajectory. It exists because the planets are always moving. Earth and Mars are not always on the same side of the Sun. Earth and Venus are not always aligned conveniently. The geometry of the solar system is in constant graceful motion, and there are periods when the planets align in ways that make a transfer orbit efficient, and long stretches when they don't. For Mars, launch windows open approximately every 26 months. Each window lasts several weeks. Miss it, and you wait more than 2 years for the next one. But when the window opens, the trajectory is relatively forgiving. The ellipse that connects Earth and Mars is wide, and there is flexibility in exactly when, within the window, you choose to launch. For Venus, launch windows open more frequently, roughly every 19 months. At first glance, this sounds like an advantage. But here is the problem that mission planners discovered in painful detail. During the early years of the space age, the Venus trajectory is far less forgiving. The geometry of Venus transfers is tighter, more sensitive to small errors in launch timing, more demanding in terms of the precision required for the spacecraft to arrive at the correct angle for orbital insertion or surface landing. The margin for error is narrower. The spacecraft must be more precisely aimed, more carefully timed at a target that is moving faster and is wrapped in an atmosphere that will destroy almost anything not specifically engineered to survive it. And then there is the question of the journey home. This is perhaps the most underappreciated factor in the entire Venus versus Mars equation, and it shapes the future of human exploration in ways that go far beyond any single mission. For a crewed mission to Mars, the return trip follows a similar Hohmann transfer in the opposite direction. The crew lands, conducts science, and then waits for the next favorable launch window, which opens after roughly 18 to 26 months on the surface before firing their ascent vehicle and beginning the long arc home. The total mission duration for a crewed Mars journey under current planning assumptions is roughly 2 to 3 years. For a crewed mission to Venus, the surface mission as we now understand it is essentially impossible with any foreseeable technology. No human could survive on the surface. The landers we've sent there survived for minutes, so any crewed Venus mission would have to be either a flyby swooping past without landing gathering data from orbit, or the extraordinary concept of a cloud altitude habitat, which we'll explore in its own time. But even a Venus flyby mission carries a specific challenge that reveals another layer of the orbital mathematics, a free return trajectory. The kind of path where a spacecraft can, if something goes wrong, simply continue its arc and return to Earth without additional propulsion is much easier to design for Mars than for Venus. The geometry of Mars orbits allows for trajectories where Earth's gravity can recapture the spacecraft naturally after a certain arc. For Venus, the geometry is less cooperative. The planet's proximity to the Sun and its faster orbital velocity makes designing abort options more technically complex. During the Apollo 13 emergency in 1970, when an oxygen tank exploded on the way to the Moon, the crew used a free return trajectory to swing around the Moon and come home. That option existed because the Moon's position relative to Earth made it geometrically accessible. For a Venus mission, designing equivalent safety margins requires more fuel, more engineering, and more mission complexity. Have you ever thought about how much of space exploration is essentially a problem of timing, of being in the right place at the right moment, at the right angle, not just in space, but in the history of technology, in the readiness of civilization, to send people somewhere they've never been? There is something quietly philosophical about launch windows. They are not obstacles exactly. They are invitations offered by the solar system on its own, schedule accepted or missed, based on whether the humans on the ground are ready. The Soviet Venera program accepted those invitations, repeatedly launching during window after window throughout the 1960s and 70s, and their engineering grew more sophisticated with each attempt. The first Venera landers were crushed or burned before they could return any data. Later ones survived long enough to transmit images. Each mission was a conversation with a planet that didn't particularly want to be visited. The Americans, meanwhile, were learning their own lessons from launch windows, but directed toward Mars. Mariner 4, launched in November 1964 during a Mars window, returned the first close-up images of another planet in July. 1965, 21 photographs of a cratered, apparently dead landscape. Scientists who had hoped for a geologically active world, perhaps even evidence of the canals that astronomer Percival Lowell had famously and incorrectly mapped in the early 1900s, were sobered. Mars was not the lush, canal-crossed world of imagination, but it was legible. Those craters, that reddish plain, those windswept dunes, they were a surface that could be studied, mapped, understood. A place where a lander could theoretically survive. A place where a human being properly protected might one day stand and look back toward the small blue dot in the sky. Venus offered no such legibility from orbit. Its surface, hidden beneath permanent cloud cover, was invisible to optical cameras. It took radar mapping first from Earth-based observatories, then from the Magellan spacecraft in the early 1990s to reveal what lay beneath those clouds. And what Magellan found was a world reshaped by catastrophe, a surface almost entirely covered by volcanic plains, with few impact craters suggesting the entire crust had been repaved by a global volcanic event somewhere between 300 and 500 million years ago. Venus had essentially erased its own history. And here is a lesson that goes beyond rocketry, beyond orbital mechanics, beyond launch windows and fuel budgets. A destination worth traveling to is not just a place you can reach. It is a place that has something to tell you when you arrive. A place whose history is written in its landscape, readable in its rocks, legible in the layers of time, preserved in its surface. Mars kept its records. Crater by crater, lakebed by lakebed, volcanic slope by volcanic slope. Mars preserved 4 billion years of history in a form we can read, sample, analyze. Venus burned its diary. And the mathematics of space travel, the Hohmann transfers, the launch windows, the fuel equations, the free return trajectories. These are not just engineering constraints. They are, in a quiet way, the solar system's own sorting mechanism. They reward patience. They reward destinations that are worth the wait. The geometry of getting somewhere is inseparable from the question of why you want to go there at all, which brings us naturally to the surface of Mars itself, and to what that ancient rust-colored landscape has been whispering to scientists for decades. Not just in the abstract language of craters and plains, but in something far more specific, far more tantalizing, and far more relevant to the oldest question human beings have ever asked about the universe: whether something like us could have existed somewhere else. There is a canyon on Mars so vast that if you placed it across the United States, it would stretch from New York City to Los Angeles and still have room to spare. It is nearly 4,000 kilometers long. In places, it plunges 7 kilometers deep. Its walls rise like the sides of a wound that never healed, carved not by water, not by wind, but by the planet's own crust tearing itself apart billions of years ago in a geological event so violent it reshaped an entire hemisphere. And yet, standing at the rim of that canyon, if you could stand there, you would be looking not at destruction, but at a library. Every layer of rock exposed in those walls is a page. Every mineral deposit is a sentence. Every ancient lake bed at the canyon's floor is a paragraph in a story that Mars has been quietly holding undisturbed for 3 to 4 billion years, waiting for someone to come and read it. That canyon is called Valles Marineris, and it is one of the reasons, one of many quiet and accumulating reasons, that Mars won the long argument about where humanity should point its rockets next. Now, before we go further into the geological memory of the red planet, if you're finding these journeys worth staying awake for, even just a little longer, a like on this video is a small thing that means a great deal. And if you'd like these stories to find you, automatically a subscription and a gentle tap on the bell will do exactly that. No pressure, just an open door. Now, let's keep reading. The story of why Mars speaks to scientists so deeply begins not with a canyon, but with a mineral. In 2004, NASA's Opportunity rover, a 6-wheeled geologist the size of a golf cart originally designed for a 90-day mission, rolled across a plain called Meridiani Planum and found something that made scientists stop breathing for a moment. Small spherical grains of hematite, hundreds of them scattered across the surface like tiny ball bearings, half buried in the reddish dust. Hematite iron oxide can form in several ways. One of them is volcanic. Another is through prolonged exposure of iron-rich rock to liquid water. The spheres at Meridiani Planum, which the mission team affectionately named blueberries, were consistent with the second process. They appeared to have formed in a watery environment, soaking slowly in iron-rich liquid that precipitated the mineral out over long periods of time, the way a cave stalactite grows one slow drip at a time. This was not proof of life. It was not even proof that the water was warm or present long enough to support anything living, but it was proof of something that, in the search for life beyond Earth, is the essential prerequisite. Mars once had liquid water on its surface. Not as a brief transient film, not as a theoretical possibility, as actual standing liquid lakes, rivers, possibly shallow seas, persisting long enough to chemically alter rock to deposit minerals in patterns that only sustained aqueous environments produce. And here is the detail that separates Mars from every other world in our solar system in terms of what it can tell us. Mars preserved the evidence. Venus, as we explored, repaved its own surface in a catastrophic volcanic event that erased virtually everything that came before. The Moon has no atmosphere and no geology beyond the slow gardening of micrometeorite impacts. Mercury is geologically quiet, airless, and close enough to the Sun that any volatile chemistry was driven off long ago. The outer planets are gas giants with no accessible solid surface. Their moons, Europa and Enceladus, are scientifically fascinating, but their potential liquid water is locked beneath thick ice shells kilometers deep, requiring drilling technology we don't yet possess. Mars is the one world in our solar system with a solid, accessible surface, a preserved geological record spanning billions of years, and direct mineralogical evidence of past liquid water, all within reach of robotic landers and eventually human explorers. That combination is extraordinary. It may be unique in the inner solar system. Let's stay with the water story for a moment, because it is richer and stranger than most people realize. The evidence for ancient Martian water comes from multiple independent lines of research, and each one adds a different dimension to the picture. There are the valley networks. Seen from orbit, vast regions of the Martian southern highlands are dissected by branching channels that look unmistakably like river systems. Tributaries feeding into larger valleys carved by flowing liquid over millions of years. These are not the result of volcanic processes or wind erosion. Their branching patterns, their cross-sectional shapes, the way they connect uplands to lowlands, all of it points to rainfall and runoff, the same processes that carve river systems on Earth. There are the phyllosilicates. These are clay minerals, minerals that can only form through prolonged contact between water and rock. NASA's Mars Reconnaissance Orbiter, using its CRISM spectrometer, has mapped phyllosilicate deposits across vast regions of the Martian highlands, in deposits that date to the Noachian period, roughly 4.1 to 3.7 billion years ago. On Earth, we find similar clay deposits at the bottoms of ancient lake systems. On Mars, they cover thousands of square kilometers. There are the deltas. In Jezero Crater, the landing site chosen for NASA's Perseverance rover, precisely because of what orbital imagery revealed there is a fossilized river delta, a fan of layered sediment perfectly preserved, deposited by a river that once flowed into a lake that once filled the crater. From orbit, it looks almost identical to river deltas on Earth. The same geometry, the same layered structure, the same unmistakable signature of sediment carried by flowing water and deposited as the current slowed. Perseverance landed in Jezero Crater in February 2021, and since then, it has been doing something no robotic mission had ever done before collecting and caching rock cores for eventual return to Earth. Those cores drilled from the ancient delta sediments from the crater floor from volcanic rocks that can be radiometrically dated represent what may be the most scientifically valuable collection of extraterrestrial samples ever assembled, waiting for a future return mission to bring them home. Have you ever thought about what it would mean to hold a rock from Mars in your hands? Not behind glass in a museum, not analyzed remotely by an instrument millions of kilometers away, but actually in a laboratory on Earth, subjected to every analytical technique science has developed over a century of geology and chemistry and biology. The potential locked in those small cylinders of Martian rock is almost impossible to overstate. But the water story on Mars doesn't end in the ancient past. It has a modern chapter too, and this is where the story becomes genuinely strange. In 2015, NASA announced that its Mars Reconnaissance Orbiter had detected dark streaks on certain Martian slopes, streaks that appeared seasonally growing longer in warm months and fading in cold months, flowing downhill in patterns consistent with liquid water or brine. They were called recurring slope lineae, or RSL. The announcement made headlines around the world. Liquid water on Mars, not ancient, not fossilized, but current seasonal flowing today. The interpretation was controversial from the beginning. Follow-up analysis suggested the streaks might be caused by dry granular flows, sand and dust cascading downhill rather than liquid. The debate continues with evidence accumulating on both sides. Most researchers today lean toward the dry explanation for most RSL features. But the conversation itself, the fact that Mars presents us with features ambiguous enough to seriously consider contemporary liquid water, speaks to the richness of the planet's ongoing science. And in 2018, another announcement, The Marsis radar instrument aboard the European Space Agency's Mars Express orbiter detected a reflective layer approximately 5 kilometers beneath the South Polar ice cap, a signature consistent with a subglacial lake of liquid water, kept liquid by the pressure of the ice above, and possibly by the planet's residual geothermal heat below. A lake beneath the ice of Mars. Small perhaps, hypersaline, perhaps more brine than water, but liquid today on a world we call dead. The science is contested. Other researchers have proposed alternative explanations, that the radar reflections could come from certain types of clay minerals or volcanic rocks, rather than liquid water. But the fact that the debate exists at all, that the data is rich enough to require serious consideration of liquid water, on present-day Mars is itself a measure of how much Mars still has to offer science. Now, contrast all of this with Venus. Venus has no preserved river valleys. Its surface is geologically young, 300 to 500 million years old, completely repaved by the volcanic catastrophe that ended whatever earlier history it might have held. There are no clay mineral deposits detectable from orbit because the surface temperatures are too high for phyllosilicates to be stable. There is no polar ice cap beneath which liquid water might lurk. There is no landing site anywhere on Venus that offers the kind of readable, layered, chemically informative geology that Jezero Crater offered Perseverance. The question isn't just whether Venus had water in its past, though it likely did briefly during its earliest history. The question is whether that history is accessible, whether the record survived, whether there is anything left to read, and the honest answer is not on the surface, not in any form we can currently reach. This is a profound scientific asymmetry between two worlds that, in raw distance from Earth, are nearly equivalent. One is an open book, dusty and ancient, but legible, its pages preserved by cold, dry air and geological stability. The other is a book that was thrown into a furnace 1 billion years ago, and what survives is only ash. There is a lesson here that extends beyond planetary science, and I think it is worth sitting with quietly for a moment. The value of a destination is not determined by how easy it is to reach. It is not determined by how bright it appears from a distance. It is determined by what survives there, what has been preserved, what can still be read by those willing to make the journey. Mars kept its receipts. It stored its geological transactions in layers of sediment and clay, and carbonate in dry riverbeds, and fossilized deltas in the carefully preserved stratigraphy of impact craters and volcanic highlands. 4 billion years of planetary history, sitting quietly in the cold and the dust waiting. And scientists slowly mission by mission, rover by rover, spectrometer, reading by spectrometer, reading, have been reading it. But here's what makes the next chapter of this story so unexpected, so quietly stunning. The question of what Mars's geological record means for the possibility of life doesn't depend only on whether ancient Mars was warm and wet. It depends on something far more specific, on what kinds of chemistry were possible, in what kinds of environments for how long. And to understand that, we have to follow the science from the surface down into the rocks, into the sediments, into the chemistry of ancient Martian water itself. Because what Perseverance and Curiosity have found in the mineral chemistry of Martian rock is not just evidence of water. It is evidence of the specific kinds of water chemistry that on early Earth gave rise to the conditions where life first appeared. The story of Mars and the story of life's origins on Earth turn out to be the same story told on two different planets, separated by 225 million kilometers, converging on the same question. And that convergence changes everything about why we're going there and what we hope to find when we finally arrive in person. In 1970, a Soviet cosmonaut named Andrian Nikolaev landed back on Earth after 18 days in space and could not walk. Not because he was injured, not because anything had gone wrong with the mission, but because 18 days of weightlessness had quietly, systematically dismantled the physical infrastructure his body had spent a lifetime building. His bones had begun to thin, his muscles had begun to waste, His cardiovascular system had partially forgotten how to pump blood against gravity. He had to be carried from the capsule. 18 days. Now, in Zhao, imagine what 9 months in space would do each way. Because that is the minimum duration of a crew journey to Mars. And the human body, it turns out, is not a passive passenger in a spacecraft. It is a second spacecraft, biological, adaptive, fragile in ways that engineers cannot bolt titanium plates over or seal with heat-resistant foam. And understanding what space does to that inner vessel is one of the most underappreciated reasons why Mars demands so much more of us than the simple distance on a chart ever suggested. If these quiet explorations of science and space are a place you return to, if they help the night feel a little more open, a little more full of wonder, like in a subscription, are small gestures that help these stories reach more people who might need them. I'm genuinely grateful for every one of you who stays. Now, let's go deeper. The story of the human body in space begins in a serious scientific sense, not with astronauts, but with dogs. On November 3, 1957, the Soviet Union launched Sputnik 2, and inside it a small mixed-breed dog named Laika became the first living creature to orbit Earth. Laika did not survive the mission. The technology to return her did not yet exist. And she died from overheating within hours of launch, a fact the Soviets did not publicly acknowledge for decades. But her flight proved something fundamental. A living body could be placed in orbit. The question that followed was whether it could survive there and for how long. The early answers were cautiously optimistic. Yuri Gagarin orbited Earth once in 108 minutes in 1961 and landed in apparently good health. John Glenn orbited 3 times later that year. The Mercury and Vostok missions demonstrated that short-duration spaceflight was survivable. The Gemini missions extended that to 2 weeks. The Apollo missions took humans to the moon and back in about 8 days. But the deeper questions, the ones relevant to interplanetary travel, required longer exposure. And as mission durations extended, the findings grew steadily more sobering. Bone loss. In microgravity, the mechanical stress that normally stimulates bone maintenance disappears. The skeleton, which on Earth is constantly being remodeled in response to the loads placed on it by gravity and movement, begins to demineralize. Early studies on Skylab astronauts in the 1970s found bone density losses of roughly 1% per month in weight-bearing bones, the spine, the hips, the femur. That rate is similar to what happens to elderly people with severe osteoporosis, 1% per month. Over a 9-month transit to Mars, that's potentially 9% of bone mass in the most critical load-bearing structures. Enough to significantly increase fracture risk. Enough to make the physical demands of landing and working on a planetary surface genuinely dangerous for a body that has just spent 3/4 of a year floating. Muscle atrophy. Without gravity to work against, muscles weaken rapidly. The leg muscles, the postural muscles of the back and core, the heart itself, which is a muscle and which in weightlessness no longer has to work as hard to circulate blood upward against gravity, all begin to diminish. Astronauts on the International Space Station exercise for roughly 2 hours every day specifically to counteract this effect, using specially designed resistance equipment that simulates the mechanical loads of gravity. Even with that, regimen muscle loss occurs. Fluid shifts. On Earth, gravity pulls body fluids, blood, lymph, cerebrospinal fluid preferentially downward. The body has adapted to this over millions of years of evolution, maintaining higher blood pressure in the lower body than the upper. In space, that gradient disappears. Fluids redistribute toward the upper body and head. Astronauts frequently report feeling congested, as though they have a permanent head cold. Their faces puff, their legs thin, and more significantly, the increased fluid pressure around the brain may press against the optic nerve, causing a condition called spaceflight-associated neuroocular syndrome, or SANS. SANS is one of the most actively studied and genuinely concerning discoveries of recent space medicine research. Analysis of astronauts returning from long-duration ISS missions has found structural changes in the eye flattening of the back of the eyeball, changes in the optic nerve sheath, shifts in visual acuity in a significant fraction of crew members. Some of these changes appear to persist after return to Earth. For a crewed Mars mission lasting 2 to 3 years total, the implications for crew vision, and therefore for the crew's ability to perform critical tasks on the Martian surface, are not yet fully understood. Now, hold all of that in mind for a moment and consider a specific comparison. A crewed mission to Venus, even a flyby, even without landing, would expose the crew to roughly similar transit durations, 3 to 5 months outbound a period near Venus, several months returning. The radiation and physiological challenges of the journey would be comparable in type, if somewhat different in degree, to a Mars mission. But here is the critical difference that the human body introduces into the Venus equation. After a Mars transit, the crew arrives at a planet where they can land, where they can stand on solid ground, where gravity, 38% of Earth's weak but real, begins immediately to reverse some of the physiological deconditioning of the journey, where they can walk, carry weight stress, their bones and muscles against a genuine gravitational field. The surface of Mars, for all its harshness, offers the human body something it desperately needs after months in space resistance: load, the mechanical stimulus of weight. After a Venus flyby, the crew arrives at a planet they cannot approach. They swing around it from a safe distance point. Their instruments gather their data and begin the long arc home. There is no landing, no rehabilitation on solid ground. The body that has spent months in microgravity returns to microgravity for the return journey and arrives at Earth potentially 2 years after departure, in a state of deconditioning that would make even the assisted exit from the capsule an act of significant physical courage. The surface of Mars is medicine. The orbit of Venus is not. But the physiological challenges of a Mars mission extend beyond bone and muscle and fluid. They include something that cannot be counteracted by any amount of resistance exercise or fluid management, and that is radiation. Space is not empty. It is filled with high-energy particles, protons, and heavy atomic nuclei accelerated to near-light speeds by supernova explosions across the galaxy, streaming through the solar system in a constant invisible rain called galactic cosmic rays. The Sun adds its own contribution through solar energetic particle events, sudden bursts of radiation released during solar flares and coronal mass ejections. On Earth, we are protected from most of this radiation by two things: the planet's magnetic field, which deflects charged particles, and the atmosphere, which absorbs them. On the International Space Station, astronauts are still partially protected by Earth's magnetic field. The ISS orbits within the magnetosphere, which provides significant shielding. On the Moon, that protection largely disappears. On a transit to Mars or Venus, it is almost entirely gone. Galactic cosmic rays are particularly difficult to shield against. Unlike the lower energy radiation from solar events, which can be blocked by relatively thin layers of material, GCRs are so energetic that adding more shielding can actually make the problem worse as the particles interact with the shield material and produce secondary radiation showers. Current spacecraft designs offer no practical solution to GCR exposure during long transits. It is one of the most pressing unsolved problems in human spaceflight. The estimated radiation dose for a crewed Mars mission, approximately 900 millisieverts for a round trip under current assumptions, exceeds the lifetime exposure limits currently set by NASA for astronauts. That limit exists because radiation damage increases the lifetime risk of cancer, and at some threshold, the risk becomes unacceptable under occupational safety standards. NASA has been working to revise those limits to develop better radiation monitoring, to investigate pharmaceutical countermeasures, but the fundamental physics has not changed. And here is the Venus comparison that rarely gets discussed. Venus is closer to the Sun than Earth. Radiation intensity follows an inverse square law. It diminishes with the square of the distance from the source. At Venus's orbital distance, solar radiation intensity is approximately 1, 9 times higher than at Earth, and roughly 2.6 times higher than at Mars. A crewed Venus flyby mission spending time in the inner solar system, closer to the Sun, would face higher solar radiation exposure than a Mars mission of equivalent duration. The galactic cosmic ray component is roughly similar throughout the inner solar system. It doesn't vary greatly between Venus and Mars distances, but the solar component, including the risk of being caught in a solar energetic particle event, is meaningfully higher near Venus. So the closer planet is also in terms of radiation, the more dangerous transit. Have you ever considered how much of human space exploration is essentially a negotiation between ambition and biology? Between what we want to reach and what our bodies can survive to reach it? There is a scientist named Scott Kelly who spent 340 days continuously aboard the International Space Station, the longest single space flight by an American astronaut at the time. His identical twin brother Mark, also an astronaut, remained on Earth. After Scott returned in March 2016, NASA conducted the most comprehensive study of long-duration spaceflight effects ever undertaken, comparing the two brothers genetically identical, one of whom had spent nearly a year in space. The findings were remarkable in their nuance. Scott's telomeres, the protective caps on chromosomes associated with cellular aging, had actually lengthened in space, then shortened rapidly after return settling below their pre-flight length. His gene expression had shifted with changes in hundreds of genes related to immune function, DNA repair, and cognitive performance. His gut microbiome had changed. His carotid artery walls had thickened slightly. Some changes reversed on return to Earth. Others persisted for months. A small number appeared to be permanent. A year in space had changed him at the molecular level. A Mars mission would require 2 to 3 years. A human body sent to Mars and returned to Earth would come back different in ways we are only beginning to understand. And yet, and this is the part that researchers at NASA SpaceX and space medicine laboratories around the world hold on to, with quiet determination, none of these challenges are categorically insurmountable. Bone loss can be partially counteracted. Muscle atrophy can be managed. Radiation risks can be reduced through careful mission timing, through pharmaceutical interventions, under active research, through spacecraft design that uses water and food stores as radiation shielding. Vision changes can be monitored and potentially treated. The body that lands on Mars will be weaker than the one that left Earth, but it will be on a planet with gravity, and gravity quiet and steady and insistent will begin its slow work of restoration. The human body is not designed for space, but it is designed for adaptation. It has been adapting to new environments for 200,000 years, to deserts, to Arctic tundra, to high altitude, to the deep ocean. Mars is simply the next environment on that long, improbable list. Venus offers no such adaptation. Its surface is not a challenge to overcome. It is a wall. And so, the journey to Mars becomes, in part, a journey of understanding what we are made of, not just as a species with ambitions and rockets and spacecraft, but as biological creatures whose bodies carry the entire evolutionary history of Earth. Inside every bone, every cell, every carefully regulated chemical gradient. The question of whether we can survive the journey to Mars is inseparable from the question of whether we can understand ourselves well enough to protect what we are while reaching for something we have never been. And that question, the question of what we're actually reaching for when we point our rockets at that small red light in the night sky, turns out to have a history that is far older than NASA, far older than rocketry, far older than the space age itself. It is a history written not in launch manifests or mission reports, but in novels, in newspaper headlines, in the dreams and fears of ordinary people across more than a century. A history that shaped not just what we believe about Mars, but what we chose to believe, and why those choices still echo in every budget meeting and mission planning session held today. 50 kilometers above the surface of Venus, something unexpected happens. The crushing pressure disappears. The temperature drops to something a human body could theoretically tolerate. The sky, if you could call it that, becomes almost familiar, almost breathable. And for a small group of scientists and engineers who've spent years thinking carefully about this, that altitude represents not a curiosity, but a genuine question. What if we never tried to land on Venus at all? What if we tried to float above it instead? It is one of the most audacious, most quietly beautiful, and most technically terrifying ideas in the history of space exploration. And the fact that serious scientists at NASA have written serious technical papers about it, complete with mission architectures, atmospheric entry profiles, and habitat designs, tells you something important about how desperately the human imagination wants to find a way to reach Venus, even after everything we know about what waits below. If the way these stories make space feel close and quiet and full of wonder is something you value, like a subscription, a gentle tap on the bell, these small things are what keep this channel alive and growing. I'm grateful for every one of you drifting through these ideas with me. Now let's float. The concept has a name, HAVOC, High Altitude Venus Operational Concept. It was developed by a team at NASA's Langley Research Center, and a detailed feasibility study was published in 2015. The lead researcher Dale Arney and his colleague Chris Jones presented a mission architecture that was methodical, technically rigorous, and if you read it with the right kind of attention, quietly visionary. The core insight of HAVOC begins with a number 0.9. At an altitude of approximately 50 to 55 kilometers above the Venusian surface, the atmospheric pressure is roughly 0.9 atmospheres, nearly identical to Earth's sea level pressure. The temperature at that altitude ranges from about 0 to 75 degrees Celsius, depending on local conditions and time of day, which is warm, but within the range that engineered systems and properly suited humans could manage. The radiation environment filtered by the thick cloud layers below is actually somewhat similar to what you'd experience on Earth's surface. For comparison, standing on the surface of Mars, the planet we've been discussing as the viable destination, requires a pressure suit capable of handling an atmospheric pressure of roughly 0.006 atmospheres, temperatures that swing between -80 and +20 degrees Celsius, and a thin atmosphere that provides essentially no protection against ultraviolet radiation. Mars's atmosphere is 95% carbon dioxide, and so thin it cannot support liquid water on the surface under any current conditions. In terms of raw environmental parameters at the habitable zone, the upper atmosphere of Venus is arguably closer to Earth-like conditions than the surface of Mars. This is the fact that stops people when they encounter it for the first time, and it stopped the HAVOC team too long enough to ask the question seriously. The mission concept they developed unfolded in phases. First, robotic exploration unmanned airships deployed into the Venusian atmosphere to characterize conditions, test materials, validate aerodynamic models. Then, a crewed flyby of Venus with astronauts spending time in Venusian orbit without descending. Then, in the most ambitious phase, a crewed mission involving astronauts entering the atmosphere in an aeroshell, deploying a solar-powered airship, inflating it during the descent, and establishing a temporary habitat at cloud altitude. The airship itself would be a helium-filled blimp, roughly 130 meters long, about the length of a modern cruise ship. Solar panels on its upper surface would generate power, since at cloud altitude Venus receives abundant sunlight. The crew would live and work inside a gondola, suspended beneath the envelope, conducting atmospheric science, deploying instrument packages, and potentially in the long-term vision, beginning to explore the possibility of a more permanent presence. The concept is elegant. The engineering challenges are, to put it gently, formidable. The atmosphere of Venus at cloud altitude is not merely warm and pressurized. It is also composed of sulfuric acid droplets suspended in carbon dioxide, The clouds of Venus are not water vapor clouds like those on Earth. They are dense aerosols of concentrated sulfuric acid, corrosive enough to dissolve many metals and polymers, to degrade rubber seals, to attack virtually every conventional material used in aerospace engineering. The Havoc team acknowledged this directly. Any airship envelope, any external surface, any instrument housing would need to be made from materials specifically resistant to sulfuric acid corrosion, fluoropolymers, certain ceramics, specialized coatings. Some of these materials exist. Some would need to be developed. The engineering is not impossible, but it is demanding in a way that goes beyond the challenges of Mars surface missions, which primarily have to contend with cold temperatures, low pressure, and abrasive dust. There is also the question of what happens if something goes wrong. On Mars, a crude habitat is on solid ground. If the pressurization fails, if a system breaks down, the crew has the surface beneath them, the stability of a fixed structure, the option in an emergency of EVA repair of contingency protocols developed from decades of experience building structures on Earth. The surface is unforgiving, but it is there. In the upper atmosphere of Venus, the habitat is floating, always moving. Subject to the extraordinary dynamics of Venusian atmospheric circulation, winds at cloud altitude that reach 300 kilometers per hour, carrying the entire cloud deck around the planet in just 4 Earth days. A catastrophic failure of the airship envelope does not mean a habitat that can be repaired. It means a descent into an atmosphere that will destroy everything before it reaches the surface. There is no abort option that involves landing on Venus. There is no rescue mission that can retrieve crew from the Venusian surface. The safety margins for a cloud-altitude Venus mission are in their current conception narrower than almost anything humanity has attempted in space, including Apollo, including ISS assembly, including the Mars missions being planned for the 2030s and 2040s. Have you ever thought about the difference between a dream that is worth having and a dream that is worth pursuing right now? Between an idea whose time has not yet come and one whose time may never come at all? The Havoc concept lives in that uncertain space. It is worth having. The science it could produce direct sampling of the Venusian atmosphere in situ, measurements of cloud chemistry, atmospheric dynamics studied from within rather than from orbit would be extraordinary. Venus's atmosphere holds genuine mysteries. In 2020, a team of astronomers announced the detection of phosphine gas in the Venusian cloud deck, a molecule that on Earth is associated with biological processes, though it can also be produced by certain geological and chemical reactions. The announcement was controversial, subsequently disputed, then partially re-examined, and the debate continues. But the fact that a credible signal of an unexpected atmospheric chemical was detected in the one region of Venus that could theoretically support aerial microbial life was enough to make the scientific community pay serious attention. The idea of life floating in the clouds of Venus, microscopic organisms drifting in the sulfuric acid aerosols, metabolizing sulfur compounds, never touching the surface. Their planet is one of the most extraordinary hypotheses in contemporary astrobiology. Carl Sagan and Harold Morowitz proposed it in 1967 in a paper published in Nature long before the Havoc concept existed. They calculated that the upper Venusian atmosphere, for all its acidity, contains enough energy and raw chemical material to support a photosynthetic ecosystem if the organisms were sufficiently acid-tolerant. On Earth, we have found acid-tolerant microorganisms, acidophiles, thriving in environments far more hostile than most life could manage. Ferroplasma acidermanus lives in mine drainage with a pH close to 0. Picrophilus torridus grows in soil so acidic it would dissolve your skin. Life, as the astrobiologists say, finds a way not everywhere, not easily, but with a persistence that has surprised researchers every time they have looked somewhere they didn't expect to find it. Does life exist in the clouds of Venus? Almost certainly not. The evidence does not support that conclusion today. The phosphine detection has not been confirmed. The chemistry of the cloud environment presents challenges even for the most extreme acid-tolerant organisms we know. But the question cannot yet be definitively closed. And a question that cannot be closed is a question that demands eventually a mission designed to answer it. Here is what makes the havoc concept and the cloud life hypothesis so significant in the context of our larger story. Tonight they represent Venus's strongest remaining scientific argument. Not the surface is closed, inaccessible, geologically young, and chemically hostile. But the atmosphere, that layered, complex, chemically rich atmosphere, still has things to say. Still holds data we have not gathered. Still presents phenomena we do not fully understand. And yet, for all the scientific value of Venusian atmospheric science, the cloud altitude habitat concept remains for now a vision, a concept study, a paper published in a conference proceedings, not a funded mission with a launch date. The gap between the idea and its realization is enormous, measured not just in dollars and engineering challenges, but in the absence of a clear pathway to sustainability, to crew safety, to the ability to return. Mars has a pathway. Imperfect, incomplete, still being built, but real. Missions are flying. Hardware is operating on the surface right now, drilling rock cores and flying experimental helicopters and demonstrating oxygen production from Martian atmosphere. The pathway is visible even if the destination is still years away. Venus has a concept. Beautiful, audacious, genuinely worth preserving and pursuing in the long arc of space exploration history. But a concept is not a roadmap. And this difference between a roadmap and a concept, between a plan and a dream, turns out to be shaped not only by engineering and science, but by something older and more human, by the stories we told about these worlds, before we ever sent a single spacecraft toward either of them, by the culture that formed around Mars and Venus over a century of imagination, fiction and popular mythology, a culture that influenced which missions got funded, which ideas captured, political will. Which planet became the one that felt to the people controlling the budgets worth the extraordinary cost and risk of human exploration? Because science does not happen in a vacuum. It happens inside a civilization. And civilizations do not invest their resources based purely on orbital mechanics and mineralogical data. They invest based on stories, on symbols, on the quiet weight of a century of dreaming in a particular direction. And the story of how Mars won that cultural argument, how it captured the imagination of scientists and writers and politicians and engineers in a way that Venus never quite managed, is one of the most fascinating, most human, and most underappreciated chapters in the entire history of our relationship with the night sky. In the autumn of 1938, on the night before Halloween, a young radio broadcaster named Orson Welles sat in front of a microphone in a Manhattan studio and read a science fiction story about Martians invading Earth. He read it as a news broadcast, interrupting fictional dance music with breathless emergency bulletins, describing alien war machines rising from impact craters in New Jersey, reporting the collapse of human defenses, the fall of cities, the end of civilization, as listeners knew it. And across the northeastern United States, some people believed it was real. They called police stations. They fled their homes. They wrapped wet towels around their faces against imagined poison gas. A bus station in a small New Jersey town filled with people trying to evacuate before the Martians arrived. No one in the entire history of radio broadcasting ever caused that kind of reaction by announcing that Venus was attacking. Think about that for a moment, because it tells you everything about the cultural geography of our solar system and how that geography shaped the choices of the space age before the first rocket ever left the ground. If these journeys through science and history and the quiet strangeness of the universe give you something worth holding on to, as like a subscription, a small gesture of saying these things genuinely matter to this channel and to me, I'm glad you're here. Now, let's go back to where it all began. The story of how Mars captured the human imagination and why Venus never quite managed the same begins not with a radio broadcast, but with a telescope and with a man whose name has become almost synonymous with beautiful, confident, completely wrong science. His name was Percival Lowell. He was an American astronomer, businessman, and writer born in 1855 to one of Boston's most prominent families. He had the money to build his own observatory, which he did in Flagstaff, Arizona in 1894, and the confidence to announce his findings to the world without excessive qualification. What Lowell believed he saw through his telescope was a network of straight lines crossing the Martian surface. Canals. Not natural features, canals, clearly artificial, clearly engineered, clearly the work of an intelligent civilization attempting to move water from the polar ice caps to the dry equatorial regions of a dying world. The Italian astronomer Giovanni Schiaparelli had first reported similar features in 1877, using the Italian word canali, which means channels not necessarily artificial ones. Lowell took the word, translated it as canals, and built an entire civilization around it. He wrote 3 books: Mars, 1895, Mars and its Canals, 1906, and Mars as the Abode of Life, 1908. In them, he described a Martian civilization, old and wise and melancholy, engineering their water distribution networks with a desperate ingenuity as their planet slowly died. He mapped hundreds of canals, gave them names, described their seasonal variations, interpreted the dark areas of the Martian surface as agricultural regions, vegetation following the water through the canal system from poles to equator. He was wrong about all of it. The canals were optical illusions, the human visual system straining to resolve detail at the edge of telescopic resolution, connecting unrelated surface features into lines that were not there. Modern Mars orbiters, with resolutions of centimeters per pixel, have found no canals, no artificial structures, no evidence of any intelligent engineering on the Martian surface. But Lowell's Mars was not primarily a scientific claim. It was a story, and it was a magnificent story, vivid melancholy, humanizing, deeply resonant with late Victorian anxieties about civilization's decline and what an intelligent species does when its world begins to fail. H.G. Wells read Lowell, and in 1898 he published The War of the Worlds, a novel in which the desperate dying Martians do not merely manage their water more cleverly. They invade Earth. They cross 56 million kilometers of interplanetary space and descend on England with heat rays and poison gas and unstoppable war machines, because their world is dying and ours is not. The novel was a sensation. It was translated into dozens of languages. It established science fiction as a genre capable of genuine literary power, and it embedded Mars into the collective imagination of the English-speaking world as a place of intelligence, danger, mystery, and existential significance. Venus in the same era received no such treatment. Venus was the featureless world, the blank face, the planet that showed nothing through even the best telescopes of the period. No surface markings, no canals, no polar ice caps. Nothing to project imagination onto, nothing to anchor a story, nothing to invite the kind of interpretive speculation that Lowell had lavished on Mars. A few writers tried. C.S. Lewis set part of his space trilogy on Venus, a water world of floating islands, verdant and Edenic. Edgar Rice Burroughs, who had already written his Barsoom novels set on a romanticized Mars, attempted a Venus series as well. But these never achieved the cultural velocity of the Mars literature. Venus didn't have a Lowell. It didn't have a War of the Worlds. It didn't have a cultural myth powerful enough to survive contact with scientific reality and emerge transformed into something that could still motivate billion-dollar space programs. Mars had all of these things, and the consequences were profound. By the time the space age began in earnest, by the time NASA was founded in 1958, by the time congressional committees were being asked to appropriate money for planetary exploration, Mars was already a character in the American imagination. It had 60 years of fictional and pseudoscientific mythology behind it. It had a face that people recognized, a name that carried weight, a symbolic significance that Venus simply did not possess. When NASA scientists argued for Mars missions, they were not arguing for an abstraction. They were arguing for a place that every American senator and representative had already encountered in science fiction, paperbacks and comic strips in the radio broadcast that had frightened people in 1938 in the cultural vocabulary of an entire generation. And science doesn't happen in a cultural vacuum. Consider the budget comparison that shaped the early space age. The Soviet Venera program, the most successful Venus exploration effort in history, was primarily funded because the Soviet space establishment believed Venus was the more accessible target and because it offered a geopolitical point of competition with the Americans. Between 1961 and 1984, the Soviets launched 16 Venera missions. They achieved extraordinary engineering feats. They became the only civilization in history to successfully operate spacecraft on the surface of Venus. And almost no one in the Western world followed the story closely. The Venera landings were not broadcast live to mass audiences. They did not generate the kind of cultural moment that Viking 1's first images from Mars generated in 1976. Photographs that appeared on the front pages of newspapers across America and Europe. Photographs that people cut out and kept photographs of a landscape that felt in some difficult-to-define way like somewhere a person might one day stand. The Viking images felt like a destination. The Venera data felt like a scientific result. The difference is not in the science. The science from Venera was extraordinary. The first direct measurements of another planet's surface chemistry, the first atmospheric profiles from within an alien environment, the first photographs from the surface of a world beyond Earth. But it arrived wrapped in the story of a world that the Western public had never been invited to imagine as a place for human beings. Have you ever noticed how the stories we tell about a place change what we believe is possible there? How a destination that exists in fiction first becomes somehow more real as an actual destination. This is not a weakness of human cognition. It is a feature. Narrative is how we rehearse possibility. It is how a civilization talks itself into attempting something that has never been done. And the narrative around Mars, built over a century of fiction and popular mythology and cultural investment, was powerful enough to survive the discovery that the canals were illusions, that there were no Martian civilizations, that the red planet was cold and dry and apparently lifeless. The story shifted, but it did not die. It became Mars is where life might have been. Mars is where life might still be in some form somewhere. Mars is where we might build something new. Mars is where the human story continues. The story around Venus shifted too, but it shifted toward closure. Venus is hell. Venus is a warning. Venus is what happens when a greenhouse effect runs away. Venus is not a destination. Venus is a cautionary tale. Both of these narratives are rooted in real science, but one of them opens a door. The other closes one. And in the 1960s, as NASA and the Soviet space program were racing to demonstrate technological supremacy, the open door received the funding, the political will, the engineering talent, and the cultural support. The closed door received extraordinary robotic missions, genuinely heroic feats of engineering, but was never seriously considered as a destination for human beings. The lesson embedded in this history is one that scientists and science communicators return to repeatedly. Because it recurs in every era, the facts alone are not enough. The data alone are not enough. Science moves in a cultural river, and the current of that river is made of stories, symbols, anxieties, and dreams that long predate any particular research program. Lowell was wrong about the canals, but his wrongness was so vivid, so richly imagined, so carefully embedded in the cultural life of his time, that it generated a century of human investment in understanding what Mars actually is. His error, in a strange and ironic way, produced more real science about Mars than any amount of correct but dry technical description might have. Venus had no Lowell. No one built a beautiful, wrong, captivating mythology around it. And when the first spacecraft revealed how truly terrible its surface conditions were, there was no cultural reservoir of romantic investment to draw on, no century of fictional Venusians and imagined cloud forests and stories of what might be waiting there. There was only data, and data without story rarely moves governments. This is not an argument that science should be distorted by narrative. It is an observation that the funding and direction of science is always at some level a cultural act. The questions we choose to pursue, the destinations we choose to reach for the missions we choose to build, these choices, are made by human beings inside a civilization, and they reflect what that civilization values, fears, and imagines. Mars became the answer to our oldest question. Are we alone? Because a century of storytelling made it feel like the place where that question might be answered. Venus became the answer to a different question. What happens when a planet goes wrong, and that question, however important, does not generate the same hunger to go there in person? But the story does not end with culture and mythology and the long shadow of Percival Lowell. Because beyond the dreams and the politics and the orbital mechanics and the human physiology and the geological record, there is the practical question of what we actually intend to do when we get there, what infrastructure we plan to build, what resources we expect to use, what it would actually take to establish a human presence on Mars that could survive, grow, and eventually become something that does not depend entirely on resupply from Earth. And that question, the question of what Mars actually offers as a place to live, as a source of the materials a civilization needs, turns out to have answers that are more specific, more encouraging, and more surprising than most people realize. On the floor of a clean room at NASA's Jet Propulsion Laboratory in Pasadena, California, in the summer of 2020, a rover the size of a small car sat surrounded by engineers in white suits and blue gloves, being prepared for a journey of 480 million kilometers. Its name was Perseverance, and tucked inside its chassis, almost as an afterthought in the engineering manifest, was a small box roughly the size of a lunchbox, an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. Its purpose was not to study Mars, not to search for life, not to photograph landscapes. Its purpose was to do something that had never been attempted on another world. It was going to make oxygen from Martian air, not carry oxygen from Earth, not store it in a tank launched from Cape Canaveral. Make it on Mars, from Martian atmosphere, the way a tree makes oxygen from carbon dioxide on a quiet afternoon in a forest on Earth. That experiment, in the context of everything we've been exploring tonight, is not just a scientific curiosity. It is the first tangible operational step toward a Mars where human beings can breathe, where rocket propellant can be manufactured locally, where the planet itself becomes a resource, not just a destination. And it worked. If you're finding that this journey, this slow drift through science and history and the quiet machinery of space exploration is worth spending your night with, liken a subscription, or the simplest way to say so. They help this channel reach more people who might need a soft place to land at the end of a long day. I'm grateful for every one of you here. Now let's build something. MOXIE ran its first oxygen production test in April 2021, 2 months after Perseverance landed in Jezero Crater. It took Martian atmosphere, 95% carbon dioxide, thin cold, laden with fine dust, and passed it through a solid oxide electrolyzer, operating at approximately 800 degrees Celsius. At that temperature, the electrolyzer split the CO, 2 molecules apart, separating the carbon from the oxygen, and collected the oxygen as a usable gas. In its first run, MOXIE produced approximately 5 grams of oxygen in 1 hour, enough to support a human astronaut for roughly 10 minutes of breathing. 5 grams. 10 minutes of air. It sounds modest. It sounds almost trivially small against the scale of what a crewed Mars mission would require. But the significance of MOXIE is not its output. It is its proof of concept. The MOXIE team, led by Michael Hecht at MIT, designed the experiment to demonstrate that the fundamental chemistry works in the actual Martian environment, with real Martian atmosphere, real Martian temperatures, real Martian dust, not in a laboratory simulation on Earth. And it did work. Across multiple runs over more than 2 years of operations, Moxie consistently produced oxygen at or above target rates in different seasons at different times of day, under varying atmospheric conditions. A full-scale Moxie system scaled up by a factor of roughly 200, the kind of system that could be landed on Mars a year or two before a crewed mission to pre-position resources could produce enough oxygen to support a crew of 6 for their entire surface stay, and enough liquid oxygen to fuel the ascent vehicle that would carry them back to orbit, not carried from Earth. Made on Mars from Mars. This is the concept engineers call in situ resource utilization, or ISRU, and it is the hinge on which the entire economic and logistical feasibility of crewed Mars exploration turns. The fundamental problem with sending humans to Mars under a conventional launch model, where everything the crew needs is packed on Earth and carried across 480 million kilometers of interplanetary space, is mass. Every kilogram of mass launched from Earth's surface to Mars costs an extraordinary amount of energy and therefore money. The fuel alone required to launch enough food, water, oxygen, and return propellant for a crew of 4 on a 2-year Mars mission under current launch technologies would be staggering. Some early estimates for fully Earth-supplied Mars missions place the total mass in the range of hundreds of metric tons, figures that made the mission economically impossible under any realistic budget scenario. ISRU changes the equation. Oxygen can be made from CO2, as Moxie demonstrated. Water ice exists on Mars, detected in abundance by orbital radar, confirmed by surface observations, present in sufficient quantities in accessible locations, near the mid-latitudes to supply a human settlement. The Martian regolith, the loose surface material. The soil contains iron oxides, silicates, and perchlorate salts that could be processed into building materials. The thin CO2 atmosphere, combined with water electrolysis, could provide the raw materials for manufacturing methane, which is both a fuel and a potential feedstock for chemical synthesis. A Mars base that can make its own oxygen breathes for free. A Mars base that can electrolyze water gets both drinking water and rocket propellant from ice. A Mars base that can 3D print structural components from local regolith builds its own walls. Each capability removes a mass penalty from the Earth launch manifest. Each capability makes the mission lighter, cheaper, more sustainable, and more independent of the supply chain that stretches 480 million kilometers back to the only planet where everything currently comes from. SpaceX's architecture for Mars colonization. Elon Musk's long public roadmap, first presented in detail at the International Astronautical Congress in 2016 and refined in subsequent years, is built almost entirely around ISRU. The Starship vehicle, designed to carry 100 metric tons of payload to Mars, would deliver not just crew and equipment, but the infrastructure for propellant production. Starship runs on methane and liquid oxygen. Both can be synthesized on Mars using water ice and atmospheric CO2 through a process called the Sabatier reaction and water electrolysis. The plan is not to land on Mars and then wait for resupply. The plan is to land on Mars and begin manufacturing the fuel for the return flight. This is a genuinely different philosophy of space exploration from anything that came before. Apollo was a flags and footprints mission, land, explore, briefly return, demonstrate capability. The Mars vision being developed now is something older and more human settlement. Establishment. The building of something that persists after the first footstep. Now, compare this to Venus. What ISRU resources does Venus offer? On the surface, nothing accessible. The temperature and pressure make any surface mining or processing operation with current technology impossible. The rocks are there presumably rich in the same silicates and metal oxides found throughout the inner solar system, but no robotic or human system we can currently envision could operate long enough on the surface to extract them. In the atmosphere, there are possibilities, but they are exotic. Sulfur compounds are abundant in the Venusian clouds and could theoretically be processed into sulfuric acid, which is already abundantly present, or into elemental sulfur. Carbon and oxygen are available in the CO2. Water is not directly present in meaningful quantities at cloud altitude. The raw materials for ISRU on Venus are less accessible, less varied, and less compatible with the specific needs of a human presence than the raw materials available on Mars. More fundamentally, Venus has no solid ground on which to build. An aerial habitat at cloud altitude has no foundation. It cannot grow. It cannot accumulate infrastructure. It cannot become anything more than a temporary floating station, entirely dependent on resupply, with no pathway toward the kind of self-sufficiency that makes a permanent human presence conceivable. The solid ground of Mars, cold, thin-aired radiation, exposed geologically quiet, is paradoxically the most important resource the planet offers. Because ground means permanence. Ground means construction. Ground means the slow, patient accumulation of infrastructure that eventually becomes a civilization. Have you ever thought about what the word settlement really means at its deepest level? It doesn't mean visiting. It doesn't mean exploring. It means choosing a place, deciding it is worth the work of staying, and beginning slowly, imperfectly, with enormous effort and uncertain outcome to make it home. NASA's current architecture for human Mars exploration, as outlined in the Moon to Mars program and updated in recent years, envisions a phased approach. First, the Artemis program returns humans to the Moon, not as a destination in itself, but as a proving ground for the technologies and operational procedures that a Mars mission will require. Long-duration lunar surface habitats, lunar ISRU demonstrations, lunar resource mapping. The Moon, as a dress rehearsal close enough to Earth that crew can be returned in days if something goes wrong, far enough to test the systems that will need to work perfectly 480 million kilometers away. Then, in the 2030s and 2040s under current planning assumptions, though timelines in human spaceflight have a long history of slipping the first crewed Mars missions. Initially short-duration surface stays of perhaps 30 days, focused on demonstrating landing habitation, EVA operations, and ISRU in a crewed context. Then longer stays of 300 to 500 days, time to take advantage of the launch window alignment. Then perhaps the first elements of a permanent outpost, the Ingenuity helicopter, the small, roughly 8-kilogram rotorcraft, that was carried to Mars as a technology demonstration aboard Perseverance, flew its first powered flight on another planet in April 2021. It was designed for 5 flights. As of late 2023, it had completed more than 70. It demonstrated that powered aerial flight is possible in the Martian atmosphere, thin as it is roughly 1% of Earth's sea level density, opening the possibility of aerial reconnaissance and eventually aerial transport on Mars. These are the details that accumulate into a roadmap, not a dream, not a concept study, but a sequence of demonstrated capabilities, each one building on the last, each one narrowing the distance between the Earth that launches and the Mars that receives. And here is what makes this moment in history genuinely extraordinary, in a way that is easy to miss when you're living inside it. For the first time in human history, the plan to send people to another planet is not hypothetical. It is not science fiction. It is not the optimistic projection of a distant future. It is an engineering program with specific vehicles under construction, specific technology demonstrations underway, specific mission architectures under active development at multiple space agencies and private companies simultaneously. The Starship vehicle has conducted multiple integrated test flights. NASA's Space Launch System has successfully flown. The ESA, JAXA UAE, and Chinese space agencies all have Mars orbiters or rovers operating right now. The infrastructure of Mars exploration has never been richer, more diverse, or more capable than it is at this exact moment in the history of civilization. And Venus, for all its proximity, for all its scientific value, for all the audacity of the Havoc Cloud habitat concept, has no equivalent program, no crewed mission in development, no ISRU demonstration planned, no habitat prototype being tested, no pathway that leads from today's robotic missions to a day when a human being floats in the Venusian clouds. The gap between the two planets is not ultimately about distance. It never was. It is about what we've built, what we've planned, what we've chosen to invest in, what we've allowed ourselves to believe is possible. And all of those choices, the funding decisions, the mission architectures, the technology demonstrations, the political will flow downstream from something that most people never think about when they consider the question of why we go to Mars instead of Venus. They flow from the cumulative weight of everything we've explored tonight, the geology that preserved its history, the chemistry that welcomes ISRU, the physics that makes it survivable, the culture that made it imaginable, the biology that makes it, if not safe, then at least survivable enough to attempt. But even with all of that, the roadmap, the hardware, the Moxie demonstrations, the Ingenuity flights, the Perseverance rock cores, waiting in their sealed titanium tubes in Jezero Crater, there remains a question that science alone cannot answer. A question that reaches beyond orbital mechanics and atmospheric chemistry and launch windows and ISRU, yield rates into something quieter and more fundamental. Not whether we can reach Mars, but why we should. What we are hoping to find when we get there, what we are hoping to become in the trying, and whether the answer to the oldest question in the universe, the question of whether life exists anywhere but here, might finally, after billions of years of waiting, be within reach of the hands and minds and hearts of a small, improbable species, from a blue planet who looked up one night at a faint red light in the sky and decided for reasons that were never entirely rational that it was worth going there. There is a photograph taken on February 14th, 1990, that changed how scientists think about everything. Voyager 1 had been traveling away from Earth for more than 12 years. It had completed its primary mission, flybys of Jupiter and Saturn and their moons years earlier, and was now heading toward the edge of the solar system, moving at roughly 17 kilometers per second through the vast, cold, almost perfectly empty space between the stars. At the request of Carl Sagan, NASA commanded Voyager 1 to turn its camera back toward the inner solar system one final time before the camera was shut down forever to conserve power. The resulting image showed a scattered mosaic of deep space with faint bands of scattered light crossing the frame artifacts of the sun's glare hitting the camera lens at that angle. And in one of those bands of light, barely visible, barely distinguishable from noise, was a pale blue dot. That was Earth. A pale blue dot 0.12 pixels across, suspended in a beam of scattered sunlight 6 billion kilometers from the camera that photographed it. Carl Sagan wrote about that image in words that have been read by millions of people since. He described every human being who ever lived, every king and peasant, every act of cruelty and courage and love, every religion and ideology, every species ever born on this world, all of it contained on that pale blue dot, that mote of dust suspended in a sunbeam, alone in the vast darkness. And he asked quietly what that image says about our responsibilities to one another and to the fragile world we share. But there is a question Sagan did not ask in that particular passage, a question that he spent much of his life pursuing in other ways. The question that lives just beneath the surface of every Mars mission, every planetary exploration program, every moment a spacecraft camera points outward into the dark. What if it isn't only blue? If these quiet hours of science and story and wonder are something you carry with you, like a subscription, a small gesture of connection, these things genuinely matter, and I'm grateful for every one of you who makes this channel part of your night. Now, Let's go all the way to the edge of the question. The search for life beyond Earth is the oldest scientific question that has not yet been answered and the most consequential one that ever will be. Not because life elsewhere would change the physics of the universe, or alter the orbital mechanics of the solar system, or rewrite the chemistry of carbon and water and amino acids, but because the discovery of even a single microbial fossil in the sediments of an ancient Martian lake bed, a cell wall, a carbon isotope signature, a molecular pattern too specific to be explained by chemistry alone, would transform every philosophical, religious, and scientific framework through which human beings understand their place in existence. We would know for the first time and with certainty that life is not a miracle unique to Earth, that it arises under the right conditions wherever those conditions exist, that the universe is not empty of what we are made of. And the implications of that knowledge, quiet, scientific, almost humble in their simplicity, would echo through every subsequent generation of human thought in ways that are impossible to fully anticipate. This is why Mars matters in a register that goes beyond geology and ISRU and launch windows and orbital mechanics. This is the question beneath all the other questions, and Mars is the place where it might be answered. The scientific case for life having existed on Mars, not life today. Not little green men, but microscopic life billions of years ago, when Mars was warm and wet, is not a fringe hypothesis. It is taken seriously by mainstream planetary scientists for reasons that follow directly from what we have explored tonight. Early Mars during the Noachian period between roughly 4.1 and 3. 7 billion years ago, had liquid water on its surface. It had a thicker atmosphere than today, providing some greenhouse warming. It had active volcanism, providing energy and chemical gradients, the kind of energy sources that deep-sea hydrothermal vents on Earth support today, sustaining entire ecosystems in the total absence of sunlight. It had organic chemistry. Carbon compounds have been detected in Martian meteorites and by Curiosity rover in Gale Crater. It had the basic raw materials that on Earth gave rise to life approximately 3.7 to 4 billion years ago. In other words, early Mars and early Earth were both in the same geological period potentially habitable. The conditions that gave rise to life on Earth may have existed simultaneously on Mars. The timeline is not merely suggestive, it is almost provocative in its precision. The oldest evidence for life on Earth, carbon isotope signatures in ancient Greenland rocks, possible microfossils in Western Australian chert dates to approximately 3.7 to 3.8 billion years ago. This is the same period as the late Noachian on Mars, the period during which Mars had its most Earth-like surface conditions, its most active hydrology, its richest potential chemistry. Life appeared on Earth at the earliest possible moment, essentially as soon as the surface conditions allowed it, possibly even before the heavy bombardment period that was still peppering both planets with large impactors had fully subsided. The speed of life's origin on Earth in the geological sense suggests that life does not require extraordinarily rare conditions or extraordinarily long timescales to begin. It suggests that life given the right chemistry and the right energy sources emerges quickly. If that is true, if life is an emergent property of the right chemistry rather than a miraculous exception, then Mars with its early Noachian conditions should have been capable of producing it. Did it? We do not know. We genuinely, honestly, scientifically do not know. And that not knowing is one of the most significant open questions in all of human inquiry. Have you ever sat with a genuinely open question, not a question where the answer is hidden or hasn't been found yet, but a question where the answer could go either way, and both directions lead somewhere profound? If Mars once had life and that life is related to Earth, life perhaps carried between the planets on meteorites, blasted off one surface or the other by large impacts. A process called lithopanspermia that has been seriously studied and is physically plausible, then life on Earth may not have originated here. We may be the descendants of Martian microbes. The first living thing to arise in our solar system may have arisen on Mars and traveled to Earth on a rock and founded everything that followed. If Mars once had life, and that life arose independently of Earth, life, different chemistry, different molecular architecture, a second genesis, then the universe is far more biologically active than we have imagined. Life would not be a single precious accident. It would be something closer to a law. If Mars never had life, despite having the right conditions for it, if the Noachian period passed without a single self-replicating molecule emerging from its lakes and volcanic vents, then something is missing from our understanding of how life begins. Something is harder than we think. And the silence of Mars would be in its own way one of the most important scientific results in history. All three of these possibilities are scientifically profound. All three of them change something fundamental about our understanding of life and the universe. And only one place in the solar system offers a currently accessible, preservable, returnable geological record that could distinguish between them. The rock cores that Perseverance has drilled from the ancient delta sediments of Jezero Crater, sealed in titanium tubes, carefully documented waiting on the Martian surface, may contain the answer. They may contain microfossils. They may contain molecular biosignatures. They may contain carbon isotope ratios that, when analyzed by the mass spectrometers of Earth-based laboratories, will fall in patterns that chemistry alone cannot explain. Or they may contain nothing of biological origin at all, and that null result will be its own kind of answer, incomplete, requiring more sampling, more missions, more years of patient work, but real. The Mars Sample Return Mission, a joint NASA and ESA program, is designed to retrieve those cache samples and bring them to Earth by the early 2030s under current planning, though the program has faced significant budget challenges and timeline uncertainty in recent years. The science case for sample return is among Planetary scientists essentially unanimous. There is no analytical capability that can be miniaturized and sent to Mars in a rover that approaches what can be done in a terrestrial laboratory, with the full range of instruments available there. The samples need to come home. And here's a detail that rarely makes it into popular science coverage of this program, a detail that is, I think, one of the most quietly extraordinary facts in contemporary space exploration. The Mars Sample Return Mission, if it succeeds, will be the first time in human history that material from another planet has been returned to Earth under controlled contamination-preventing conditions and subjected to rigorous biological and organic chemical analysis with the explicit goal of detecting signs of life. Every Mars meteorite we possess, and we have identified approximately 277 of them on Earth, blasted off the Martian surface by ancient impacts and eventually captured by Earth's gravity, was contaminated the moment it landed, exposed to Earth's atmosphere, Earth's water, Earth's biology for thousands or millions of years before discovery. Any biosignatures they might have contained are hopelessly entangled with terrestrial contamination. The cached Perseverance samples have never been exposed to Earth's environment. They were sealed in sterile tubes on the Martian surface under Martian conditions, and if the sample return mission succeeds, they will remain sealed until they are opened in a specially built sample receiving facility, a laboratory designed specifically to handle material of unknown biological status, with contamination controls comparable to those used in biosafety level 4 facilities. The moment those tubes are opened on Earth will be potentially one of the most significant moments in the history of science. And if the answer is yes, if there is something in those tubes that should not be there, something that looks like it was once alive, then everything we have done to reach that moment will be retroactively justified. Every Hohmann transfer calculated every Venera lander, crushed every astronaut's bone, density carefully monitored every MOXIE oxygen molecule, produced every Ingenuity flight, logged every budget meeting, endured every decade of patient incremental, unglamorous scientific work in laboratories and clean rooms and mission control centers around the world. All of it will have been the prelude to the answer. But even before that answer arrives, even while the rock cores sit waiting in their titanium tubes on the floor of Jezero Crater, and the sample return mission works through its engineering challenges, and the first crewed Mars missions are being designed in offices in Houston and Pasadena and Toulouse and Beijing, the question itself is already doing its work. It is making us look outward. It is making us think carefully about what life is, where it comes from, how fragile or how robust it might be. It is making us examine our own planet with new eyes, asking what conditions here gave rise to what we are, and whether those conditions are common or rare in the universe beyond. The search for life on Mars is not separate from the study of life on Earth. It is the same inquiry conducted from two directions at once, inward and outward, simultaneously meeting at the ancient question of origins that every human culture in every era has tried to answer in its own way. We are not going to Mars to escape Earth. We are not going to Mars because Earth has failed us. We are going to Mars because the question that Mars might answer, the question of whether we are alone, whether life is rare or abundant, whether the universe is empty or quietly, patiently full, is the question that has lived inside human curiosity since the first person looked up at the night sky and wondered what was out there. And that question, after 4 billion years of life on this planet and a century of space exploration and decades of Mars missions and all the orbital mechanics and physiological data and cultural mythology and ISRU engineering we have explored tonight, that question is at last within reach. Not answered, not yet, but within reach. Which means the only thing left to ask is this: what do we do with that reach? What kind of species do we choose to be standing at the edge of the answer? And what does the night sky look like from the other side of the question, from a future where we already know? That is where we're going now. Into the last quiet chapter of this long night's journey, the one that doesn't end with data or mission architectures or rock cores and titanium tubes, but with something older and softer and more essential than any of those things. The reason we look outward at all. There is a question that has no scientific answer. It lives beneath every mission architecture, every launch window calculation, every carefully drilled rock core, and every carefully measured oxygen yield. It is not a question about chemistry or orbital mechanics or atmospheric pressure or bone density or radiation dosimetry. It is older than all of those things and quieter, and in some ways more important than any of them. Why do we go at all? Not how. Not when, not which planet, why? Because nothing about human survival requires us to send spacecraft to Mars. Nothing about the continuation of civilization on Earth demands that we drill into the sediments of Jezero crater, or manufacture oxygen from Martian atmosphere, or design habitats that can withstand 9 months of cosmic radiation and the slow mechanical disassembly of microgravity. We could theoretically spend every dollar and every engineering hour currently directed toward Mars on problems closer to home, on hunger, on disease, on the accelerating ecological unraveling of the only world we have ever known. And yet we go. We have always gone. Not just to Mars, but outward, always outward toward the horizon, toward the unknown, toward the place just beyond the edge of the map, where the familiar world gives way to something that has never been seen. The question of why we do this is not a distraction from the science. It is the deepest layer of the science. And tonight, after everything we have explored together, I think the answer is finally ready to be said. Now, and I mean this with genuine warmth, if you have stayed with this journey from the first quiet moment to this last one, if you have drifted through 8 chapters of orbital mechanics and Venera landers and geological time and cultural mythology and rock cores and radiation dosimetry and the search for ancient Martian life, thank you. A like on this video, if it has meant something to you, is the most direct way to tell me. And if you'd like more nights like this one, a subscription will make sure the next story finds you. You can also share this with someone who might need a quiet night of wonder. Now, let's finish this together. In 1972, a geologist named Harrison Schmitt stepped onto the surface of the moon. He was the first professional scientist, as opposed to a test pilot or military aviator, to walk on another world. He was part of Apollo 17, the last crewed lunar landing mission, and he spent 3 days on the moon collecting samples describing what he saw, doing the careful observational work of a trained field geologist in a landscape no geologist had ever studied before. At one point during his moonwalk, he looked up. Above the lunar horizon, hanging in a black sky with no atmosphere to soften its edges, was Earth. Blue and white and impossibly vivid, a sphere of color in a universe of black and gray. He had trained for years for this mission. He had memorized every geological feature of his landing site. He had practiced every EVA procedure until it was automatic. But nothing had prepared him for what it felt like to look at Earth from outside it. He described it later as the most disorienting experience of his life. Not frightening, disorienting. The sense that the place he was standing was real solid present, and the place he came from was the distant one, the fragile one, the small one. You develop an instant global consciousness, he said in words that have been quoted many times since. A people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. This psychological phenomenon, the sense of profound perspective shift, that astronauts report when they see Earth from space, particularly from the distance of lunar orbit, has a name now. Researchers call it the overview effect. It was first described systematically by the writer Frank White in his 1987 book of the same name, based on interviews with astronauts and cosmonauts about the cognitive and emotional impact of seeing Earth from the outside. The overview effect is not a metaphor. It is a documented psychological response, a sudden, often overwhelming recalibration of perspective, in which the borders between nations become invisible, the fragility of the biosphere becomes palpable, and the unity of all human experience becomes not an abstract philosophical proposition, but a visceral, immediate, undeniable fact. Edgar Mitchell, who walked on the moon during Apollo 14, described looking out the window of his spacecraft at the star field and feeling without any warning or gradual approach a sudden certainty that everything was connected, that the molecules of his body and the molecules of the spacecraft and the molecules of the stars visible through the window were all part of the same story. He described it as an instant global consciousness, the same phrase Schmidt used arrived at independently. He spent the rest of his life trying to understand what had happened to him in that moment. Ron Garan, who spent 178 days on the International Space Station in 2011, wrote that looking at Earth from orbit produced a sobering contradiction between the beauty of our home and the sad state of affairs on the surface. He described the oceans as luminous, the atmosphere as impossibly thin, a film of blue barely thicker in proportion than the skin of an apple. He understood in his body, rather than just in his mind, how fragile the conditions that support all of us actually are. And here is what makes this relevant to everything we have explored tonight, relevant in a way that goes beyond the poetic. Every astronaut who has experienced the overview effect has reported that it changed how they thought about Earth, about stewardship, about the relationship between the planet and the species that lives on it, about what matters and what doesn't when you are looking at everything you have ever known from far enough away to see it whole. Now imagine that experience from Mars, not from low Earth orbit where the ISS circles at 400 kilometers and Earth fills a significant portion of the sky. Not from the moon 384,000 kilometers away, where Earth is still large enough to show continents and weather systems, but from Mars 225 million kilometers away, at average opposition distance where Earth is a pale blue dot in the Martian sky, barely distinguishable from a bright star smaller than the period at the end of this sentence, indistinguishable to the naked eye from Venus or Jupiter. What does the overview effect feel like from that distance? What does it do to a human being to look up from the red surface of another world and find Earth, all of it, every person they have ever loved, every city they have ever walked through, every ocean and mountain and forest and conflict and kindness, an ordinary Tuesday morning, compressed into a single point of pale blue light, hanging in a Martian sky the color of butterscotch? No one has experienced this yet. No human being has stood on Mars and looked back. But the people who will do so, the astronauts and scientists and engineers who will make that first landing, who will take those first steps, who will look up at that small blue light in the Martian darkness, they will be changed by it in ways that no training program can prepare them for, and no psychological assessment can predict. And what they bring back, not just the rock cores, not just the atmospheric measurements, not just the biosignature data, but the perspective they carry home in their changed minds and bodies and hearts may be among the most important things any human being has ever returned from anywhere. Have you ever had a moment, maybe not from orbit, maybe just from the top of a mountain or from a plane window at night, or from the quiet of a dark backyard with the Milky Way overhead, where the scale of things shifted unexpectedly, and you felt just for a moment simultaneously very small and very much a part of something enormous? That feeling is a version of what the astronauts describe. Smaller, closer to home, but the same species of experience, the same sudden clarity, the same quiet recalibration, the same sense that the ordinary concerns of ordinary life are real and important, but that they exist within a context so vast and so beautiful that they deserve to be held a little more lightly. Science does this to us when we let it. Astronomy does this to us when we really sit with what it is saying. The universe is 13.8 billion years old. It contains an estimated 2 trillion galaxies. The Milky Way alone contains somewhere between 100 and 400 billion stars. The number of planets in our galaxy alone is estimated to exceed 1 trillion. And on one of them, on this one, this pale blue mote of dust suspended in a sunbeam, something happened roughly 3.8 billion years ago that has not yet been confirmed to have happened anywhere else. Something began to live. And approximately 300,000 years ago, a geological eye blink, a rounding error in cosmic time. One branch of that living thing began to wonder where it came from, began to look up, began to ask questions that its own existence could not answer, began to build instruments to see further theories, to reach deeper vehicles, to go where no organism on this planet had gone before. That wondering, that reaching it, is the most distinctively human thing we do. Not language, not tool use, not social organization. All of those are shared in various forms with other species. But this particular reaching outward, this compulsion to ask what is beyond the next horizon, even when the next horizon is 225 million kilometers away and costs decades of engineering, an enormous treasure and genuine risk to human life. This seems to be ours alone. And it is worth asking quietly in the context of a night like this one, whether that reaching is a luxury or a necessity. Here is what I think after everything we have explored tonight. It is both. It is a luxury in the sense that we could survive without it. Earth would continue to turn. People would continue to be born and live and love and die and make dinner and argue and forgive each other and plant gardens, all without a single spacecraft ever leaving this atmosphere again. The species would persist. The civilization would continue. But something essential would be lost. Something about what we are capable of imagining, and therefore what we are capable of becoming. The horizon is not just a destination. It is a mirror. When we look outward at Mars and ask what life might have been there, we are simultaneously looking inward at ourselves and asking what life is here. When we design systems to sustain human beings in the harshest environment in the solar system, we are learning things about sustaining human beings that apply everywhere, including here. When we send cameras and spectrometers and helicopters to another world and share the images with everyone, on this one, we are doing something that every human civilization in every era has done in its own way, expanding the shared map of the real. The exploration of Mars is not a distraction from Earth's problems. It is a different angle on the same problems, the problems of how a species survives, how it manages its resources, how it understands its place in a universe that did not ask for its opinion and will not wait for its readiness. Venus in this light is not a failure. It is a lesson, the most vivid and specific lesson in our solar system, about what happens when a planet's climate system loses its balance. A lesson written in 465 degrees of surface heat and 92 atmospheres of crushing pressure, preserved for us in the geological record of a world that might have been our twin. We are learning to read that lesson. We are sending orbiters and designing future missions and arguing about phosphine and debating cloud altitude habitats because Venus has things to tell us. And we have not yet finished listening, and Mars is not a replacement for Earth. It is an extension of our curiosity, our reach, our willingness to ask the hardest question and to travel the longest distance in search of an answer that changes everything. Here is what we know. At the end of this long night's journey, Venus is closer in distance. Mars is closer in every other way that matters in geological legibility, in physiological survivability, in chemical accessibility, in cultural resonance, in the practical architecture of human exploration, and in the proximity of its ancient history to the question we most need answered. The choice to go to Mars instead of Venus is not a failure of imagination or a miscalculation of distance. It is the result of a century of science, engineering, culture, and human ambition converging on the one destination in our solar system where the oldest question might finally receive a reply. And that question, are we alone, is not really about Mars. It is about us. It is about what kind of universe we live in, and what kind of creatures we are, and whether the spark of life that began on this small blue planet in this ordinary spiral galaxy is a singular miracle or a universal tendency. Whether the universe is at its deepest level, lonely or full. Carl Sagan, who spent his life asking this question in every form available to him, from radio telescope surveys to planetary missions, to the golden records attached to Voyager 1 and 2, carrying the sounds and images of Earth into interstellar space, wrote in his final book, Billions and Billions, published just after his death in 1996, somewhere something incredible is waiting to be known. He did not know what it was. He did not claim to. He simply held the question open with the patience and the courage that genuine scientific inquiry requires and trusted that the asking was worth the waiting. We are still asking. We are still waiting. And the answer in a titanium tube on the floor of Jezero crater in the sulfuric acid clouds of Venus, in the subglacial lakes beneath the Martian poles, in the data from instruments not yet built on missions, not yet launched. The answer is out there. We just have to keep going. And on quiet nights like this one, when the world is dark and still and the mind is soft and open, the going feels less like a burden and more like what it actually is. The oldest, most human thing we have ever done. Sleep well, friends. Dream of pale blue dots and red horizons and the quiet, patient certainty that somewhere in the dark, something incredible is waiting to be known. Thank you genuinely from the bottom of my heart for spending this night with me, for drifting through 9 chapters of science and history and wonder and not giving up when the orbital mechanics got complicated or the bone density statistics got sobering. You are exactly the kind of curious, patient, open-minded person these stories are made for. And I hope that when you close your eyes tonight, you carry something from this journey with you, even if it's just the image of Earth as a pale blue dot in a Martian sky, held in the mind of someone standing on red ground, 225 million kilometers from home, looking back at everything they have ever loved. The next story is already waiting, another quiet corner of the universe where science and wonder meet in the dark, another chapter in the long human project of understanding where we are and what we are made of. Stay close. It will find you soon. Good night. Dream gently. The stars will still be there when you wake.